discuss two more data structures related to the previous topic, so it's kind of related to segment trees, but it's a little bit different. Let's go. So the first data structure we'll discuss is Fenwick tree. Sorry, let's take another one. What is Fenwick tree? Red-black tree? Yeah, no, it's not about red-black trees. Red-black trees is about binary search trees. Fenwick tree is something slightly in a different direction. So we will move to some. I'll explain. So Fenwick tree is not exactly a tree. It's named Fenwick tree, but we will not draw a tree in this data structure. But it may be represented as a tree, if you kind of wish. Let's go. So what is Fenwick tree? Imagine you want to have a data structure, and you want to answer two types of questions. Like before, you have some array, and you have two types of queries. First query is to change element. Second query is to find sum in a segment, like before. So first query, let's have it different way. So let's have increment element I by v. It will increment the value of one element of the array by v. So make something like this plus code. And second query is to find the sum on a segment. Like before, you just return the sum of all elements from L to R minus 1. And Fenwick tree allows you to make both these operations in log n time. So have both time complexities log n. You may kind of recognize this situation. We started with this situation in the first lecture of this semester. So in the first lecture of this semester, we had the same two operations. We had set operation, which just assign one element of the array, but it's actually it is the same situation. We have two operations. One operation is to change one element. Another operation is to find the sum on a segment. And we already learned how to do it using segment trees in log n time complexity. Why do we need another data structure? Yeah, that's a complicated question. Obvious answer is that this structure is better than the segment tree. So the time complexity is the same, but it is the same asymptotically. The constant factor is less actually in this data structure. It works faster in constant factor comparing to segment trees, but still it is better in practice. And the second thing why the structure is better than a segment tree is because it uses less memory. And that sometimes is crucial, because sometimes you kind of have a short amount of memory and you don't want to spend another like n elements of the segment tree. Well, how many elements do you need in the segment tree? In segment tree, if you have segment tree if you have array of size n, well, if you do it like we discussed in the lecture, then you actually need to increase the size to closest power of 2. Yeah. And if n is close to 1 power of 2, then you need to add another like n elements. Yeah, here. So now you have 2n elements in your array. And then you build a segment tree on top of this. And here you add another n nodes to create this segment tree. 2n. So you have 2n elements in it, and so you have something like 4n elements in your segment tree. In the worst case, yeah. So if this n is close to the power of 2, then you increase it to the next power of 2. You add another n elements. So you have 2n elements here, 2n elements here, 4n elements in total. It can be improved actually. You can modify your data structures so in such way so you don't need to increase the size of your array. So you can modify the segment tree in such a way that you don't need this, but still, even if you have n elements in your array, you need these n elements to maintain all the sums on all the segments. So the total number of elements will be 2n. So if n is small, it's not a big problem. But if n is big, so if you have like billion of elements, yeah, so you have array of size of billion. So you spend a gigabyte of data to maintain this array, and then you maintain another bigger gigabyte of information to maintain all these nodes. That maybe not what you want in your program, because you don't want to spend another gigabyte of data and spend another gigabyte of memory. So in Fenwick tree, all we will need is just one array of size n. So for this Fenwick tree, we will have just one array of size n. So basically, we don't use any additional memory comparing to the array we need. So we will not even store these elements of array A. We will just have some magical n elements, and these n elements will give us all we need to maintain these two operations. Yes, n plus 5 is asymptotically similar. No. Additional factor is additional constants is not a big problem. So let me show. So if you have n elements and n plus 5 elements, it's not a big problem. It's obviously the same. So you just spend 5 additional elements. It's not a problem. Problem is when n is big. Yes. So when n is small, it's not a problem. When you have one operation n, one data structure of size n, another of 5n, that may be hurtful, because when n is big, again, when you have n equal to billion, here you have 1 billion. You may have $1 million, or you have $5 million. Yeah, that's kind of difference. Yeah, if you have $1 million and $1 million and $5, it's not a big difference. So that's kind of the idea of this. So this constant factor may be not what you want in your program when you have a big amount of data. This plus constant is not a problem, but when you multiply by constant, it may be a problem. We usually don't talk about this because we just measure the asymptotics of the algorithm. When you discuss the algorithms, you only measure the asymptotics of the algorithm. Yeah, because when you want to specify the constant factor, you want to specify your computational model, like we discussed in the first lecture. Yeah. So when you specify your computational model, you kind of fix all the constants, and then you may want to optimize the constant factor. But it all depends on your computational model. So in theory, it's not something important, but in practice, if you optimize your memory 5 times, it is something important, because again, okay. Let's go now. So how we'll maintain Fenwick tree? We will maintain one array. Let's have array F of size n, and each element of array F will maintain some on some segment of array A. So element in position I will maintain some on a segment from something, let's say P of I to I. So we will fix some special function P. I'll explain it later. And each element of array F will maintain some segment of array A. That's all. That's the whole plan. That's the only array we will maintain. So all we need in this data structure is this array F. Now, how we will implement this data structure? When you want to calculate sum from L to R, first we'll split the sums into two sums on prefixes. So we'll say this sum is equal to sum from 0 to R minus 1 minus sum from 0 to L minus 1. Then we'll calculate these two sums separately, then subtract this from this and get the result. Now, how we'll calculate these sums? It's pretty easy. So you have this array A. Yeah? you want to calculate sum on some prefix. So you have this prefix from 0, let's say, to x. How to calculate this sum? Let's look at this element of array f. So this element of array f contains the sum of some segment like this. So look at this position in array f. In this position of array f, you have some segment from p of x to x. Now you add this sum to your result, and then you need to calculate sum of this prefix. So you look in this position, get this sum. Now you look in this position, get this sum, and so on. So that's the whole plan. How we'll calculate the sum on prefix? We look in this last element of array f. This element of array f contains sum on some segment of array a. So we take this sum. Now we look in this position. This position contains sum on this segment. So we add this sum. Now we look here, take this sum. Then we take sum of all these segment sums and then we get this sum on the whole prefix. Good. That's the plan. Now, how we will increment the value? So when you need to increment the value, okay, you have position I, and you want to change the value of this element. To change the value of this element, you need to recalculate sum of the segment sums. So you need to find all the segments which contains this element inside the segment. So you find basically starting from this position. So this position contains some element, then this position contains some this segment, this position may contain some this segment, and so on. So you try to find all the segments which contain element I. So you find all these segments and just increase the sum on each segment by v. Makes sense? Again, you're too quiet. Just say something at least every 30 seconds. Just to keep me it's working, right? No, stream is working. Yeah, I'm kind of nervous and stream is down, so just keep saying something. Just okay. That's good. That's the whole plan. Now, the magic part is to find a good function p such that both this operation can be done in log n time. So I just put some function p here, but not all functions are good. So if you take pi equal to I, then you will have a lot of segments here. If you take pi equal to 0, then you will have a lot of segments here. Makes sense, yeah? So you need to find some good function p, and good function means that in both these operations you have small number of segments. So you need to have a small number of segments when you calculate the sum and prefix. So this number of segments should be small. And also when you modify the element, number of these segments should be small. So I want to find some function p. So number of these segments is about log n, and number of these segments is about log n. And the whole magic is about how to find this good function p. Good. Square root of n. If you make p of I equal to, you can make it no square. You can make, let's see, if you make it equal to I minus square root of n. I think that's what you need. Yeah. So if you do something like that, then in both cases you will have square root of n. So you jump with step equal to square root of n. You have square root of n segments here, and when you update, you have square root of segments to update. So if you make this function, you will have square root of n in both cases. But I want log n. Log n is less than square root of n. Now, there is some intuition behind this, but I will show you the magic. It's easiest way to understand what's going on is just present this function and prove it is correct. You can think about how you can come to this function if you don't know this function. But I will just, for simplicity, I will just show you the function and explain why it's working. So the magic function works like this. You have this number I. Yeah. Let's look on the binary representation of this number. So number I is just some vector of bits. We will construct function p in the following way. We will look on the number I. If we have a number I, let's find the rightmost zero in its binary notation. So in this binary notation, let's find the rightmost zero. So here we have some ones, and here we have the zero. Let's find this zero. So we have this zero, we have some ones here, and here we have some prefix. The value of p of I will be calculated as follows. We'll take the same prefixes here. And we will fill all these suffixes with zeros. Like this. That's all. That's how it's calculated. Well, let's look. For example, if you have I equal to, let's say, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Then p of I will be calculated. So we find this 0. Yeah. We have the same prefix here. And we take zeros for these last bits. Again, function is very simple. You take these last ones, yeah, and change them with zeros. That's all. That's the whole plan. Good. Now, let's try to calculate this function using some bit magic. So we'll use some bitwise operations to calculate this number p of I. So how can you calculate this number p of I using some bitwise operations? So again, you have some bitwise logic, right? So you have bitwise OR, bitwise AND, bitwise XOR, and so on. Yeah. And you want to use these operations. We discussed it when we discussed some dynamic programming, right? So you want to find some magic bitwise operations which will give you this number from this number. Any ideas? But the idea is pretty simple. So you have this number I, yeah. So you need to take these last ones and change these ones with the zeros. So you need to find some another number which is kind of the same as I, but with zeros in the end. So you need some operation which removes these last ones. Any ideas? Any questions by now? Yeah. Good. So it can be calculated very simple way. You just take this number I and calculate the bitwise AND with number I plus 1. Why it's working? Because in number I plus 1 you have, so if let me show this. In number I plus 1 looks like this. Number I plus 1, you have this same prefix. Here you have 1 and a lot of zeros. Now when you calculate bitwise AND of these two numbers, you will have the same prefix here, but all zeros in these positions, because no, this position will be 0 because here is 0. These positions will be zeros because here are zeros. So all these positions will be zeros, and these positions will be the same because we have the same prefix here. That's all. So this function is very easily calculated. And now we will show that if you use this function, you can actually perform both these operations in log n time. Okay? It looks kind of like magic, but it's fine. It's the easiest way to understand what's going on. You can think about how to come up with this function. It's actually quite simple. So if you think a lot about, to find some way to, again, what do you want? You want in both these cases to have the number of segments to be log n. So if you think about how to make a number of segments about log n, you kind of need these segments to have a length of like powers of 2. So you want each next segment to be a bigger power of 2. So if you have some 1 power of 2, then bigger power of 2, so on. You think about it. That's actually interesting thing to think about, but not today. You may use I and minus I. No, I believe it's different. If you take I and minus I, you will find the closest power of 2. It's something like that, right? No, I and minus I give you something different, I think. Yes, you may build another structure which is indexed from 1. If you have the first index equal to 1, you may have some different formulas. Yeah. Good point. Now let's go. Now this is the function we need. Now let's implement these two functions. First, let's implement sum. So again, you have sum of again, you have sum of L and R. We will just return sum of R minus 1 minus sum of L minus 1, and sum of R looks like this. Again, this is the prefix of first R elements. We say X equal to R, and then we just make like this. So we take this position X, add this to the result, and move to here. So we say result equal to 0. Now while X at least 0, we increment the result by this value in position X and move to the next position. So we'll move from here to here. So X will be moved to P of X minus 1. P of X is this. So it will be X and X plus 1 minus 1. Yeah, I believe you can modify this formula. Yeah, I believe you can modify this formula to look like in your, yeah. It doesn't matter actually. You may use another bit magic to calculate this formula. And now no, just return result. That's all. That's the whole function which calculates the sum on prefix. Now let's make the second function. The second function is to increment the value. It's a little bit more complicated. So how to increment the value? To increment the value, we need to find all the segments which contains this element. So we have some. So we have this element I. We need to find. Let's write it here. So we have this element I. We need to find all j's such that. Let's just write this. We need to find all values j such that I is on this segment. So if I is on this segment, it means that P of j is less or equal than I, less or equal than j. Okay. Well, let's look what's going on here. What's going on here? So we have this number j, you have number I, you have number p of j. This is less or equal than this, less or equal than this. So this number j, this is number p of j. So these two numbers have the same prefix, like here, like here. So you have this common prefix here and here. And in number j you have zeros and some ones. In number p of j you have 0 and the same number of zeros, 5. And now we need our number I to be between these two numbers. Yeah. So how to find numbers between those? So between these two numbers, any number with this prefix. So if you take any I with the same prefix here, and then 0 here, and something here, this number will be greater or equal than this number and less or equal than this number, right? Because here you have all zeros, here you have all ones. So it will be between these two numbers. That's the whole picture. And now we need to find this number j from number I. So we have this number I in this function. So we need to find these numbers j. This number j is constructed from number I. So we take this number I, and now we take some suffix of this number and change it with all ones. So we take some bits in the end of the number I and change these all bits to ones. And that's how we will produce the number j. Well, for example, let me show you. It's this whiteboard is a little bit small for something. I tried to fit the whole family tree on whiteboard. It's a little bit too small. Okay, so let's set here. So you have this number I. Let's have some numbers like 0, 1, 1, 0, 0, 1, 1, 0, like this. Let's find all possible j's, such as find this in equation. So again, how to find this number j from number I? You need to take number I, take its suffix, change all bits to ones, and this will give you some number j. Now we'll increase the size of this suffix, so we'll add more and more ones in the end, and we will produce all possible j's, right? So how to produce all possible j's? Let's produce them from smallest to largest. So let's start from the smallest possible j. Smallest j is just equal to I. So, we will just start from number I. This is the smallest number satisfying this equation. Good. Is it clear why it's the smallest number? Because each next number will be just, you add ones to your bitwise binary notation, and when you change zeros to ones, you just increase your number, right? So the smallest number which satisfies this equation is just I. Good. And now we'll increase this number and find the next values of j. So to find next value of j, we just need to swap some zeros in the end of number I with ones. Again, you're too quiet. You're making me nervous. It's not good. So we to find the next number j, we need to find this rightmost number 0 and change it to 1. So next number j will be like this. So we find this 0, change it to 1. J always, the first value of j may have 0 in the end. but every next value of j will add zeros from right to left, because that's how it's working. So when you go from number I to j, it is the same number, but this tail is changed with ones. So we start from number I, and then add ones from the end of the binary notation of I. So each time we take the rightmost zero, change it to 1. Find the next value of j. Then to find the next value of j, again, we find the rightmost zero here and change it to 1. So we have 1, 1, 1, 0, 1, 0, 0. And then to move to the next one number, again, we find the rightmost zero, change it to 1, and so on. Now again, find the rightmost zero, and so on. So this is how we will construct all possible j's which satisfies these inequations. Yeah, good. So how to move from one value of j to the next value of j? It's very simple. We need to find the rightmost zero and change it to 1. We do it the same way as we do it here. We just calculate j plus 1 and make bitwise OR of these two numbers. So when you move from here to here, you take number j or j plus 1. Yeah. Yes, so the only value of j which has 0 in the end may be the first one. So all next j's will have last bit equal to 1, just because each time will increase number of ones in the end of the tail. Let's go, let's just implement this. So again, we'll have j equal to z to I. Now while this j is less than n, we just increment this value and we make f j plus equal v. And then move to the next value of j. J equal to j or j plus 1. Ta-da! That's the whole code of the Fender tree. So this is how you calculate the sum. This is how you increment the value. That's all. Now let's think why both these operations work in log n time. Let's start from this operation. Why this operation works in log n time? No, because each time you add one bit in your binary notation. You have up to log n bits in this binary notation. So each time you increase the number of ones. So you may have maximum log n ones in your binary notation. So this while loop works at most log n times. Log n. Same thing here. So if you look on this while, it is also increasing the number of ones. No, because when you move from we move from x to p of x minus 1. Yeah. So you move from x to p of x, so you still have this. And then if you calculate p of I minus 1, you have all these bits equal to 1. So again, when you move from I to p of I minus 1, you increase the number of 1 bits in the tail of your binary notation, binary representation. So you may increase number of these ones at most log n times. So this while also works at most log n iterations. That's all. On average, it's about log n time. You may have less than log n. You may have. No, I think on average you have like half of your bits equal to 0. So it's something log n divided by 2 on average. Same thing here. But still, if you just look on this code and compare it to the code of the segment tree we implemented on previous lectures, this code is much simpler. So all operations here are very simple operations. In the segment tree, you have all this recursion. You calculate, you sum, you go here, you go here, go to this node, go to this node. Here, just make this simple cycle. All operations are very simple, so it's actually like few times faster than the same operations in segment tree. Just because the code is simple, all operations are simple. That's because this number of iterations is actually about the same as in segment tree, but every iterations is much faster than in segment tree. Okay. Segment tree is more powerful. That's correct. In segment tree, we discussed you can do much more interesting things in segment tree. This structure, first of all, we used, then you have sum operation. So you have this inverse operation. So it only works when you have inverse operation in your sum function. So it's you can just you can sometimes, but not exactly. It's not as simple to adjust it when you don't have this inverse operation. And second, you don't have these mass operations. You cannot increment the all elements on the segment and so on. Actually, you can, but that's complicated. So it's not that simple to modify these data structures to work with other functions. So usually you just use it when you have these two functions. You can increment and you calculate sum in a second. If you have something more complicated functions, then you may want just to move to segment tree, because segment tree is very powerful data structure. You can just use any associated operations, and it will just work. Here is it's tricky. So sometimes you can adjust your data structure to work with some different functions. Sometimes it's tricky. No. You cannot do lazy propagations here, because how to make lazy propagation? Again, I think you can modify it, but you still, if you want to have lazy propagations, you need to have two arrays. So you need to have one array of these sums and another array of these propagations. And I don't know how to make propagations here, because it's not obvious. No, I think you just cannot make propagations here. Yes, because you may have up to log n children in this tree. You may think about this. Just leave it for you as an exercise. Okay. So this is the first data structure. Well, second data structure is actually more important. Second data structure is sparse table. That's cool data structure. So let's start again with the same problem. You have some array and you want to calculate some functions on a segment. But this time we will not change the array. So array is fixed, so it's called static problem. So you have the same array. This array A. And the only function you have is to calculate the sum on a segment. So you don't have this operation which changes the element of the segment. The array is always the same. All elements will always be the same. But you want to calculate the sums on some segment. So how to calculate these sums we already discussed this. How to calculate these sums when you have the static array. So when you don't need to change the elements of the array, you can actually calculate these sums without any segment trees, Fenwick trees, or anything. So if you just need iteration which calculates the sum on the segment, you can do it without any segment trees, Fenwick trees. Yes, you can just use prefix sums. Yeah. So if you want to calculate sums on a segment, you can calculate all prefix sums. Yeah. So when you need to calculate sum on the prefix, you take this prefix sum minus this prefix sum, and then calculate the sum on the segment. So you can calculate the sum on the segment in constant time. But before you can calculate this, before you can make this operation, you need to pre-calculate all the prefix sums. Yeah. So we will kind of split the time complexity into two parts. First part will be time of pre-calculation. So when we take this array and we do something to calculate some strange sums, and then we will answer the questions. Yeah. So we'll split time complexity into two parts. First part will be time we spend for pre-calculations. In this case, for example, we need to pre-calculate all prefix sums. To calculate prefix sums, we need to spend like linear time to make these pre-calculations. And then after these pre-calculations, we will answer the queries, right? And if we calculate all the prefix sums, we can answer all the queries in constant time. So in static data structures, it always works like this. So if you have some static data structure, so you don't change the state of your data structure. Time complexities is always looks like this. So you have two parts of your time complexity. First, you spend some time to prepare all your data, and then you answer queries. So you have like, you kind of want to optimize both these parts. Let's go. So if you just need to calculate the sum, it's easy. You calculate prefix sums and that's all. Interesting part is when you want to calculate some different function. For example, what's going on if you want to calculate minimums. So if you want to calculate minimum on segment from L to R. Now it's tricky. The first one you can do is just to apply the segment tree. So you may want to take segment tree, construct a segment tree, and then you can answer the queries to find the minimums in the segment. Why not? Segment tree is a perfect data structure. So how much time do you need to prepare the segment tree from the given array? So if you just have the array, how much time do you need to build the whole segment tree? I want to build this whole segment tree. It's strange segment tree, but that's fine. So I give you this array, and you need to prepare this whole segment tree. Yeah, you can build segment tree from the given array in linear time. So you just go from bottom to top, calculate all the minimums. In linear time, you will calculate. You can do it in n-log n time as well, but it actually can be done in linear time. Just iterate from bottom to top and calculate all these minimums. It will work in linear time. And if you have segment tree, you can answer all the queries in log n time, obviously. This is the segment tree. And now I will present another section. So we will talk about sparse table. Sparse table can make the same requests in form time complexity. We will build sparse table in n-log n time, but we will be able to answer all the queries in constant time. And now the question is, so this is the sparse table. Now the question is, what is better? So what situation is better? What do you think? No, it's a tricky question. It's because it depends on what's going on. So when you need to choose what data structure to use in your program, you kind of need to think how many requests do you have. So if you have m queries, yeah, then if you use segment tree, the total time complexity will be, so you spend n operations to build the segment tree, and then you use m log n operations to answer all the queries. And if you use sparse table, then you spend n log n time to construct your sparse table, and then you answer all the queries in constant time, so it'd be plus m. So when you choose which data structure to use, you kind of need to look about what is better. It depends on the number of operations. So if this number of queries is big, then you kind of need to use sparse table. If m is small, then actually this time complexity is better than this, because here we have n plus something small log n, here we have n log n plus m. So depending on the number of operations, one of these data structure may be better than another data structure. That happens. Sometimes you have several data structures and you need to choose which data structure to use in your case. Spoilers. It's actually possible to solve this problem in an optimal way. So it is possible to do this in linear pre-calculation time and constant query time. We will discuss this in few lectures, I think in like 4 lectures. So in about a month, we will discuss how to do this. So just keep it in mind. But not today. Today we'll just discuss this simple data structure. Cool? Cool. Let's go. Before we start, let's do something simple. Let's do simple data structure. Let's build this data structure with these time complexities. So if I want n squared time complexity for pre-calculation and constant time complexity for query, how to build this data structure? Can you do it? It's quite simple. So if I can spend n squared time for pre-calculations, what should I pre-calculate to be able to answer all possible queries in constant time? Yeah, in n squared time, I can pre-calculate all possible minimums. So if I have this time to pre-calculate something, I will just pre-calculate all possible minimums. So I will create array m of L and R will be minimum on segment from L to R. I will just calculate all these minimums, put them in some array, and when I need to answer this query, I just go to my array, find this value, and output this value. That's all. Quite simple plan. And now we will slightly improve this. So we'll pre-calculate minimums on some segments, but not all possible segments, but on some segments. The idea is to pre-calculate segments on only of segments of length equal to power of 2. So you have this array A again. We will pre-calculate the minimums on all possible segments with length equal to power of 2. So write this. So if you take some segment from L to R, -1. I'll just make -1 everywhere. So I want the length of the segment equal to power of 2. So I have this will be L plus 2 power k minus 1, right? And I just put all these minimums into some array. Let's say A ij will be equal to minimum. No, A. I have array A, right? Let's have array M. Minimum on segment from I to I plus 2 power of j minus 1. So, I will pre-calculate minimums on all segments with length equal to power of j, 2 power of j. Yeah? That's all. That's all. Now, 2 questions. I need to pre-calculate all these values in n log n time. And second question, I need to be able to answer all the queries in constant time using these minimums. So let's do this, both operations. First, let's try to pre-calculate all these values in n log n time. Again, how many values do we need? So here I is from 0 to n minus 1 and j is from 0 to log n. Yeah. So we have n log n values. And I want to pre-calculate all these n log n values in n log n time. So I kind of need to pre-calculate each minimum in constant time. How can I do it? It's actually easy. So let's look on the segment. So we have this segment. The length of this segment is a power of 2. So this is 2 power of j. Yeah? It's 2 power of j. How to calculate minimum on this segment? It's quite simple. We will just split the segments into 2 parts. It's called binary lifting. So you split the segments into 2 parts. You calculate minimum here, pre-calculate minimum here. So length of both the segments 2 power j minus 1. So we will calculate these minimums by increasing the value of j. So we already pre-calculated all segments of length 2 in power j minus 1. Now we take 2 such segments and calculate the minimum on this segment. Yeah, we will discuss the same operation. Actually, we will talk about binary lifting on the trees. So it's kind of common operation when you this is a way to like double the length of your step. So you calculate the value when you have this step. Now you make 2 steps. So you like increase the size of your step twice. We will use the same approach when we will talk about tree requests or about LCAs and stuff. In just again in few weeks. Now, what I was talking about? Yeah. So you just iterate over value of j. So you just. But first, if j equal to 0, so let's just iterate for I from 0 to n minus 1. The first layer of this sparse table, you need to assign manually. So you need to assign value of mi0 to ai. Yeah? So this is the minimum on a segment of size 1. So if j equal to 0, then a segment from I to I. So one element minimum is equal to ay. And now you apply this formula. So you iterate for all j from 1 to log n. Iterate for I from 0 to n minus minus 2 power of j. And then calculate this minimum. Then mij will be minimum of these 2 elements. Minimum of mij minus 1. It is this left element. Okay? It is segment from I of length j minus 1. And minimum of this segment, it will be I plus 2 power j minus 1, j minus 1. Great. That's all. That's how you pre-calculate all these minimums in n log n time. So total time complexity here is n log n. All this pre-calculation works in n log n time. Good. That's all. And now we need to calculate minimum on a given segment in constant time. So again, you have this array A. You are given some segment from L to R. And you need to find minimum on this segment. To find minimum on a segment, you do the following. Let's calculate the length of this segment. So the length of this segment will be just R minus L. Now let's find the maximal power of 2 not greater than this length. So let's find maximal k such that 2 in power of k is no more than this length. And now let's use the segment of size 2 in power of k from this left border. So let's take this segment of length 2 in power of k and calculate minimum on this segment. This segment is just m l k, right? Well, let me just write the code. No, I'll write the code later. And now we know minimum on this segment. And we need to have minimum on this segment. So we need to find minimum of these elements as well. And now we will do a very easy trick. We will take another segment of length 2 in power of k and start from here. So we will use 2 overlapping segments, each segment of size 2 in power of k. Now we know minimum here, we know minimum here. So if we want to have minimum on this whole segment, we can take minimum of these 2 minimums, and it will be equal to minimum on the whole segment. Good. Just write it here. Write it like it is the code. So we need to take of log 2 of len, and here we just return minimum of 2 values of m l k and m r minus 2 power k, like this. That's all. That's how we do it in constant time. Little bit actually this operation is something strange, because here I kind of use logarithm, and I just tell that I can calculate logarithm in constant time. It depends on what's going on. So in practice you can calculate logarithms using some process operation. So but basically you need to find for integer number the largest power of 2. So basically what you need here, you have this length, right? And you need to find the largest power of 2 in greater than. So you kind of need to find this largest one in your binary notation. So you need to find the index of this leftmost one in your binary notation. Usually your processor can do it in constant time. If it can, in theory, it doesn't matter, because you can pre-calculate these logarithms for all possible values of k. So this value of k, well, this value of len is up to n. So you can pre-calculate for all possible lengths this k. So you can just make another array which will give you the good value of k for given value of len. This len is up to n. Yeah, so you can make array of logarithms for each value of len. You can pre-calculate this array in integers in linear time, so it doesn't matter. But usually it's not a problem. Usually you can just calculate this. Minimums in Fenwick tree is complicated. You can talk about it. You can think about it, but the problem is Fenwick usually works with some prefixes. So when you calculate on segment, you can just split minimum into parts. There are various techniques. Just try. Usually the easiest thing is not to use Fenwick trees when you need to find minimums. This usually is not worth it, but you can try. Do we have time? Oh, we have time. That's all. Yeah. Let's try to use the same technique for different operations. So this technique is only useful when you have minimum function. And we kind of use that the function is exactly minimum when we calculate it here. So here we can use any operation, right? Here you can apply any associative operation and it's fine. So you can. Here we didn't use any special properties of minimum, but here we did. Here we use a special property of the minimum, and especially we use that you can overlap these two segments here and calculate minimums for these elements twice, and it will be the same as if we have each element exactly once. It happens because minimum is the important operation, yes. Because if you have minimum of x and x, it will be equal to x. And it is the same, basically, here you need the operation to be, let me think, you need it to be commutative and idempotent. And if it like a minimum, because I calculate value from here to here, then I move here, calculate to here, and I have the same value. So if you have commutative idempotent operation, that's fine. For example, you have binary or, binary and, greatest common divisor, stuff like this. Again, all the stuff which looks like minimums. If you have any operation like this, then you can apply all this technique to this operation. What happens if you don't have these properties? So if you have some usual associative operation, can you do it in the same way? It turns out actually you can. So we can achieve the same time complexity for any associative operation. Actually, even better than complexity, but not today. So if you take any associative operation, so let's say calculate from L to R. We'll try to do the data structure with the same time complexity for any associative operation, like in segment trees. Let's go. So how to do it? That's kind of complicated. So let's go. What is the plan? May I erase this? Okay. I hope you don't have any questions. Okay. I hope you didn't have questions about this, because I'm gonna erase this. Okay. I need some space, sorry. Let's go. So let's do the following. Let's have some array. Let's have array of the size power of 2, just for simplicity. So let's have some array of 8 elements. So this is array A. First, let's split array in the middle. So let's play array here, split the array here. So we split array into two halves. It's like divide and conquer technique. Very simple. Split array, and then we recursively will go do the same. Very simple. So we split array here, and now we calculate the sums on all suffixes here and all the prefixes here. So we calculate the sum on these segments, on all segments like this and all segments like this. I'm explaining the same data structure with the same time complexity, but for any associative operation. So I want to have sparse stable time complexity for any associative operation, not only for minimums. That's the plan. So we split array here, calculate all these sums, calculate all these sums. I can do it in linear time, right? So I just calculate these sums from right to left, calculate this sum plus this sum plus this sum plus this sum, and so on. And in the same way, I calculate these sums, calculate one element plus this sum plus this element, this sum plus this element, this sum. So I can calculate all these sums in linear time, put them in some array. Good. Now I can answer a lot of different queries. So now if someone asks me to find sum on some segment, so if you want to calculate sum on this segment, you can just look in your array and find two pre-calculated sums. So you find this pre-calculated sum and this pre-calculated sum. Then you take this plus this will be equal to the sum on your segment. And you can do it in constant time. Yeah. So again, you are given some segment from L to R. You look in your pre-calculation array, find the sum on this segment from L to middle, and sum on this array from middle to right. Yeah? Take sum of these two segments, and you will get the sum on the whole segment. Pretty simple plan. Clear enough. Let's have some real array. Let's have some array. Let's say 5, 2, 1, 6, 3, 5, 4. So this is array A. I will use function plus just for simplicity. You can do it for any operation. So I will have operation plus. So I will calculate sum on a segment. It's kind of strange because I can calculate sum in constant time, but just for simplicity, okay? So I want to calculate, to be able to calculate sums on some segments. No, I can use product, but sum is simpler, okay? So I'll use sum. So I want to calculate sum on some segments. Again, I split this array here, calculate sums on these segments, calculate sums on these segments. Well, these sums will be 6, 7, 9, 14. And here the sums will be 7, 10, 15, and 19. So I can do it in linear time. I calculate these sums from right to left, these sums from left to right. These are just prefix sums and suffix sums. It's easy. Now, then I need to answer the query. When I need to answer, so I want to find sum on this segment. I find the sum on this segment here and sum on this segment here. So now I take this plus this. So for this segment, the total sum will be 7 plus 15. So the result will be 7 plus 15 equals 22. That's all. Now, this all works. Then this segment intersects the middle of the array, right? So if the left border of the segment is in the left half of the array, and the right border is in the right part of the array. If you have segment like this, so it's completely inside the left part of the array, then I cannot do the same trick, yeah, because I cannot split the segments into two and pre-calculate. So I don't have this sum pre-calculated. So what to do when the segment is inside one of the halves of the array? Just do the same. We do the same thing recursively. So we'll pre-calculate the same thing for the left part and the same thing for the right part. For the left part, we split the left part in two and try to pre-calculate sums on these segments. So we have these segments and these segments. And for the right part, we have split in two and calculate sums on these segments and these segments. No, I cannot subtract. No, if I have some operation, if I have plus, I surely can subtract. But if your operation is not reversible, you cannot subtract. I just show it for plus operation because it's easier. Imagine you cannot subtract, just for simplicity. So you don't have minus operation in your language. You only have plus. So that's what we want to do. So we calculate these sums, So these sums will be 2 and 7. These sums will be 1 and 7. And here we have 3 and 10. And here we have 5 and 9. And now again, if your segment intersects this middle point, then you can construct the sum on your segments using two sums like this. So you go here, you take this segment plus this segment, and you will get the result you need. If it's not, then again, you split your segments into parts, go on the next level. On the next level, you have something, you have just one element. You have this split here, this split here, this split here, this split here. So you have these four segments of size 2. You split each segment into the parts. So you have 5, 2, 1, 6. That's all. So you need 3 layers of recursion. So this is layer 0, this is layer 1, layer 2. On each layer, you have n elements. You can pre-calculate all these n elements in linear time. So you have here you have log n layers, and on each layer you have n numbers. You can pre-calculate them in linear time. So total time of pre-calculation will be n log n. So you can pre-calculate all these values in n log n time. And now when you need to answer the query, how to answer the query? You need to find the smallest layer such that your segment intersects the middle on this layer. So on each layer you have this special point. So on this layer you have this special point. On this layer you have these special points. On this layer you have these special points. So for your segments you need to find the smallest layer such that you have some of these special points inside your segments. And if you do, then you just go to this layer, find these two segments, combine them, and get this sum on your segment. That's the whole plan. Now, how to find the corresponding layer? There are different techniques. The most easy technique works like this. Let's have this one. So you have number L, number R. Let's look on their bitwise representation. Like here all indices have 3-bit numbers. So we have indices from 0 to 7. They have 3 bits. So we have this left index and right index. They both have 3 bits in binary representation. What do you not really connect to sparse table? It's kind of have the same time complexity. The structure is pretty different, right? The structure is different, but time complexity is the same. Now, let's look on these 2 borders of your segments. How to find out if your borders are on different sides of this position. So if your left border is here and your right border is here, what does it mean? It means that your first bit of your binary representation is different, right? So here you have 0 and here you have 1. So if the leftmost bit is different, then on the first layer of your structure, you will find your answer. And if both an L and R go in the same half of this array, then the first bit will be the same. So if you have L and R here, then you will have first bit of L and R 0, and second bit will be different. So if the first bit is different, then you will find your result in the first layer. In the second bit is different, you will find your result in the second layer, and so on. So to find the corresponding layer, you need to find the leftmost bit, which is different than L and R. And bit of L and R. So how to find the leftmost different bit? It's easy. You calculate XOR of this bitwise XOR of these 2 numbers, and then if in this bitwise XOR find the leftmost one. So calculate this L, this is R. So if you calculate L XOR R, so here we have the same prefix. Here we have 0, here we have 1. So if you calculate XOR, you have a lot of zeros here, and here we have 1. So you just need to find the leftmost one in the bitwise representation of XOR of this L and R. That's the easiest way to do this. There are more complicated way which doesn't involve any bitwise magic. It's also possible. You can do it without any bit magic, but it's kind of more complicated. No, it's actually easy. Let me show you. You can do it just, you need to find for this segment the smallest layer which intersects this layer. So you can just build the following. So you can, for each position, you build the layer which intersects this position. So like you put 0 here, you put 1 here, you put 2 here. And now to find your layer, you just need to find minimum on the segment. That's the easiest way, which doesn't need any bit magic. So you just create this array. Again, this array corresponds to these split points, and for each split points you put the layer corresponding to this split point. And now you need to find the smallest split point in your segment. So it's just minimum on this segment. And we already know how to calculate minimums. So we use this to calculate minimums in constant time. Now we'll find the layer, and in this layer we use these 2 sums to calculate the sum on the segment. That's another way to do it without any bit magic. That's all. Oh, we actually fit in time today. Okay, let's do it again. Okay, if you ask. So what I want to do, I want to have data structure which will allow me to find the value of some bit operation, associative bit operation on any segment. Yeah, like the same like in segment tree, but the array never changes. So array is static, And we have operation which calculates the value on the segment. So how can we do it? We will combine the value of the segment from two pre-calculated segments. So we will always have two pre-calculated segments. We will combine these two values and have the sum on the whole segment. So how to find the segments we need to pre-calculate? We will use some divide and conquer technique. So we will find the middle point of our array. Then in the left part, we pre-calculate sum on all suffixes, and here we pre-calculate sum on all prefixes. Now, if we in this query, if we ask to find some sum on segment which contain this middle point, let me write it again. So if the request contains this middle point, then we can combine these segments from two segments, and for both segments we pre-calculated the value. So we have pre-calculated value here, or the pre-calculated value here, pre-calculated value here. So we take this sum plus this sum, and it will be the result for this segment. If this segment does not contain this middle point, then it belongs to one of the halves of this array. So we do the same thing recursively. We do the same thing recursively here and here. So again, we split each segment into two halves, pre-calculate suffixes here, prefixes here, suffixes, prefixes, and so on, until we reach the point when we have segments of size 1. And so now when we're given some segment, we find the smallest layer which contains the middle point. And then we calculate our sum just around this middle point. So we take some suffix, some prefix, and the sum will be equal to sum on your segment. What do you mean disjoint sparse tables? What does it mean? No idea. It actually can be improved, like we discovered on the lecture on Wednesday. You can achieve actually better time complexity just using simple ideas. You can split your segment not in one segment, not in halves, but in separate segments. So you can split your segment not in two parts, but in many parts. So this depth of this recursion will be smaller, and you actually can achieve much better time complexity. So you can just get rid of this log n factor and change it with Ackermann function. But it's complicated. I will not do it today. Can we try to code this? It's actually quite easy to code. Really, it's really easy. So easiest way to do is the following. You just take your array, right? Then iterate on all layers. For each layer, you don't make any recursion here. Just simple for cycles. So you iterate on all layers. For each layer, you iterate on all these middle points just by simple for loop from left to right. So go from left to right, find these middle points. For each middle point, you iterate to the left, one for loop to calculate these suffixes, another for loop to calculate these prefixes. So we have one for loop, second for loop, third for loop. We have 3 fors. That's simple, and that's all. That's how we calculate this. Just try it. It's actually very simple data structure. And when you answer the query, you calculate XOR of this L and R, find the leftmost one. It will give you the number of the layer. Then you go to this layer, find these two elements just by indices. Yeah, you have index of this element, index of this element. So you find these two indices, find these two sums, make plus, and that's the results. It's actually very easy data structure. You can implement it like in, I think, like 50 lines of code, maybe less. I think 30 lines of code. Yes. If you want to do what I was talking about, so if you want to get rid of this logarithm, you need to split your segment into several segments. Well, let's just do we have time? Yes. Just for the final thoughts. So if you split your segment into several segments, what you can do, what you need to do, you need to be able to answer queries which so you want to be answer queries like this. To answer queries like this, you need this suffix, this prefix, and sum on these segments. So you may pre-calculate all prefixes, all suffixes, and then you need some data structure which allows you to calculate sum on blocks. So you have some blocks. On each block you can pre-calculate the sum, total sum of all elements in block there. And now you need to calculate the sum on segment of blocks. Well, for example, if the size of this block is log n, then you have n over log n blocks. And now you can use the same data structure to calculate prefix sums on blocks. No prefix sums, or sums on segments of blocks. So you just use the same technique to calculate sums on these blocks. That's all. And now you can answer all the queries which have borders in different blocks. And if borders are in the same block, you do it recursively. Something like that. That's a little bit more complicated. But that stuff is very simple. Okay, that's all for today. Next week we will start to talk about binary search. No. Next week we will talk about two-dimensional requests. Yes, sweep lines and stuff. And then we'll move to binary search trees. That's the plan.